What is autocorrelation? One of the assumptions of the classical linear regression model is that conditional on X, the successive error terms are independently distributed. If the regression model is yi is equal to beta 1 plus beta 2 x2i, so on up to beta k xki plus ui, then the above assumption basically implies that covariance between ui and uj is equal to expected value of mu I or expected value of ui uj equal to 0 for all I not equal to j. This property of the error term is known as serial independence or no autocorrelation. Autocorrelation, also called as serial correlation, is therefore said to be present in the regression model when this assumption is violated. So what we are saying is that if covariance between mu I and uj is not equal to 0 for some I not equal to j, and expected value of ui uj is not equal to 0 for some I not equal to j, then we have the violation of the assumption. So what is the meaning of autocorrelation? In an intuitive sense, when no autocorrelation is present, the magnitude and sign of the error term for some observation should not influence the sign and magnitude of the error term in the adjacent observation or observations. This implicitly implies that the different observations in a data set are unrelated to each other. So, for example, if we have data on income and consumption expenditure of individuals, then the consumption expenditure of the ith individual has no influence on the consumption expenditure of the I plus first individual. So presence of autocorrelation, on the other hand, would imply that the various observations are correlated to each other. So the observations in the data set may not only be treated as data points, but also as predictors for the subsequent observations. So for example, in a study of output, an unexpected event like breakdown of machinery will decrease the output for a particular observation. But this negative disturbance for one observation should be no reason to have a negative disturbance for the neighboring observations. So the influence of a random disturbance should not persist over time. But if a hangover of the disturbance term is observed from one observation to the neighboring observations, then autocorrelation is said to be present. The presence of autocorrelation is troublesome in regression analysis because it reduces the number of independent observations in the data set, compounding the process of statistical inference. Now we will look at the structure of autocorrelation. We know that when autocorrelation is present, expected value of ut, comma, ut minus s is equal to gamma s, where s is equal to 0 or plus minus 1 or plus minus 2 and so on, and is the length of the leg. At leg 0, the expected value of ut square is the constant variance term. Let variance of ut is equal to expected ut square is equal to sigma square, which is also denoted as equal to gamma 0. Autocorrelation at leg s, rho s may be defined as rho s equal to gamma s upon gamma 0, where S is equal to 0, plus minus 1, plus minus 2, so on. Now this is equal to gamma S upon sigma square, because as we said earlier, gamma 0 is equal to sigma square. Therefore, covariance ut and ut minus S is equal to gamma S is equal to sigma square into rho S. The symbol plus minus before the number of lags indicates that the gammas and rhos are symmetrical in S, and it does not matter whether the lag is t plus S or t minus S. So these coefficients are constant over time and depend only on the length of the lag. For a sample with n observations, the variance covariance matrix of the disturbance term may be written as follows, which is variance of u is equal to variance of u1, covariance of u1, u2, so on, up to covariance u1 to un. In the second row, we have similarly covariance u2, u1, variance u2 up to covariance u2, un, so on. And our last row in the matrix is covariance un, comma u1, covariance un, u2 up to variance un. So in this matrix, you can see in the diagonals, we have the variances of u1, u2, un, and in the off diagonal elements, we have covariances. So this matrix variance u can be written also is equal to gamma 0, gamma 1 up to gamma n minus 1. In the second row, we can write it as gamma 1, gamma 0 up to gamma n minus 2, so on. And the last row can be written as gamma n minus 1, gamma n minus 2, so on up to gamma 0. So again, in the diagonals, we have gamma zeros, and in the off diagonal elements, we have gamma 1 to gamma n minus 1. This matrix variance of u is therefore equal to sigma square into the first row, which is 1, row 1 up to row n minus 1, and the last row is from row n minus 1, row n minus 2 to 1. I can also define this as sigma square into the matrix with the first column from 1 to element to row n minus 1 element. The second column can be written from row 1 to row n minus 2, and the last column of this matrix is from row n minus 1 up to 1. Estimation of this matrix is not possible since the number of unknowns is greater than the number of observations. In the literature, a structure is imposed on the disturbance terms to estimate this matrix. Now, let us study the process of generating autocorrelation. In time series data, three types of simplified structures may be imposed. The first structure is the autoregressive process, also known as AR process, which is an autoregressive process is one where u is a function of lagged values of itself. The second characteristic is when ut is a function of its own value with one period lag, then it is known as first order autoregressive or AR1 scheme. In case of AR1, ut is equal to phi ut minus 1 plus epsilon t. This is our equation 1, where phi is some parameter such that modulus phi is less than 1 and epsilon t is white noise disturbance term with the usual properties, that is, epsilon t is distributed normally with mean 0 and variance covariance as sigma epsilon square, and covariance between epsilon t and epsilon s is equal to 0 for all t not equal to s. In general, a pth order autoregressive, or known as ARP, scheme may be defined as follows, which is ut is equal to phi 1 ut minus 1 plus phi 2 ut minus 2 plus so on up to plus phi p into ut minus p plus epsilon t, where phi I modulus value is less than 1. And let me repeat, epsilon t is distributed normally with the 0 mean and variance, which is sigma square epsilon. And covariance between epsilon t and epsilon s is equal to 0 for all t not equal to s. Usually, an AR4 process is apt for describing the disturbance term in seasonally non-adjusted quarterly data. Similarly, AR12 may be quite suitable for describing the disturbance term in seasonally non-adjusted monthly data. The second type of structure is the moving average process, denoted as MA process. A moving average process is the one where U is a function of epsilon. A first order moving average process MA1 is given by ut equal to theta 1 epsilon t minus 1 plus epsilon t, where epsilon t again is distributed normally with mean 0 and variance sigma e epsilon square, and covariance between epsilon t and epsilon s is equal to 0 for all t not equal to s. In general, the pth order moving average MAP scheme is given by ut equal to theta 1 epsilon t minus 1 plus theta 2 epsilon t minus 2 plus so on till theta p epsilon t minus p plus epsilon t, where epsilon t as usual is distributed normally with mean 0 and variance sigma epsilon whole square, or sigma square epsilon, and covariance epsilon t and ts is equal to 0 where t is not equal to s. And the third structure is joint autoregressive moving average process, also known as ARMA process. A general ARMA process is given by ut equal to phi 1 mu ut minus 1 plus phi 2 ut minus 2 so on till phi p ut minus p plus theta 1 epsilon t minus 1 plus theta 2 epsilon t minus 2 so on plus theta p epsilon t minus p plus epsilon t. Now we will study how autocorrelation looks like. For a AR1 process defined in our equation 1, the autocorrelation function, or ACF, is given as rho s is equal to phi raised to the power s, where s is 0, 1, 2. And for AR2 process, the ACF is given as rho s is equal to phi 1 row s minus 1 plus phi 2 row s minus 2 comma and s is greater than 0. Stationary conditions ensure that the ACF is a decaying function of S. A plot of the ACS against S is known as correlogram. Moving on to the graphical view of the autocorrelation. Graphical or graphically, autocorrelation may be understood by plotting the residuals against the observations. This can be seen through the following graphs. In the graphs, you will find that panel 1 shows that a positive residual is followed by a positive residual, and a negative residual is followed by a negative residual, which is the case of positive autocorrelation. Moving on to the second panel, it shows the absence of autocorrelation because the distribution of the residuals across observations is absolutely random and does not follow any pattern. And the last panel shows the presence of negative autocorrelation because a positive residual is followed by a negative residual and a negative residual is followed by a positive residual. Now we discuss the specific causes of the autocorrelation. Autocorrelation is found more often in time series data because when the dependent and the independent variables are observed as a sequence of observations over time, then they tend to be correlated with each other over time, or sometimes related phenomenon may be influencing both the variables over time, causing them to co-vary. We will study all these causes in detail in our subsequent slides. There are several factors causing autocorrelation, starting from first the model specification, which basically means omitting a variable. Now, this may happen when some relevant explanatory variables have been omitted while specifying the model. Then their effect is captured by the residual term. It may also happen because this results in exhibiting a systematic pattern generated by the combined effect of the omitted variables creating spurious autocorrelation. Thus, a model specification bias is likely to generate an autocorrelated error term. Moving on to the second cause, which is the model misspecification, which is incorrect functional form. Sometimes a model is erroneously estimated as a linear relationship between y and x when the true underlying relationship is nonlinear. This is likely to generate an autocorrelated error term. Because it leads to overestimation and underestimation of the error term in some different ranges of data. The third cause of autocorrelation is lagged dependent variable. In this, suppose the dependent variable in a given time period is a function of its own value in the previous time period. For example, consumption in period t is equal to beta 1 plus beta 2 income t plus beta 3 consumption t minus 1 plus ut. If the lagged value is erroneously dropped from the model, then the error term would also include the impact of lagged consumption, and instead of being random, will exhibit a systematic pattern. So, autocorrelation is likely to be present in autoregressive models. Moving on to another cause of autocorrelation, which is inertia. Many variables such as consumption expenditure, industrial output, unemployment, price index, etc., when observed for several periods as time series, they tend to be suffering from inertia or known as carryover process. Now, this may be characterized by persistence, a tendency to remain in the same state from one observation to the other. They could also be characterized by business cycle behavior. Continuing with the discussion of inertia, let's starting at the bottom of a recession. At the start of economic recovery, they tend to move upwards so that each observed value will be greater than the previous observed value. Therefore, the successive observations are more likely to be interdependent, and the regression model is more likely to be characterized by an autocorrelation error term. Now, the fifth cause is known as cobweb phenomenon. Cobweb phenomenon is when a variable responds to another variable with a time lag. For example, when the supply of agricultural products reacts to price changes with a one-period time lag. For example, we can write supply T is equal to beta 1 plus beta 2 price T minus 1 plus UT. Then the disturbance term UT is not expected to be random. In fact, the error term displays a pattern of being positive in one period, followed by a negative value in the successive year, followed by a positive value, and so on. Another cause of correlation is nature of empirical study. Sometimes the empirical relationship being studied is such that the autocorrelation gets built into the system. For example, when the expectations augmented Phillips curve with adaptive expectations is used to explain the phenomenon of inflation, then the expected inflation in the current year is forecasted as the value of inflation in the previous year. Another such example is the returns from hedge funds. The returns from hedge funds are strongly correlated with their values in the past. Because these securities are not very actively traded in the stock market and their market prices are not always readily available, so their reported returns are calculated on the basis of their past returns, leading to correlated observations across time. Next cause of autocorrelation is data transformation. Sometimes the given observations are transformed to generate a data set which is more suitable for the desired empirical analysis in the following ways. First is using averages. A quarterly series may be produced from a monthly series using the process of averaging. The second is extrapolation or interpolation. Data may be obtained by extrapolation or interpolation when it is not available for certain time periods or observations. Third is difference equation. If a model is given as ut is equal to theta 1 ut minus 1 plus epsilon t, which is our equation 1, then our model is yt is equal to beta 1 plus beta 2 xt plus ut, equation 2. Then it must also be the case that yt minus 1 is equal to beta 1 plus beta 2 xt minus 1 plus ut minus 2, equation 3. Equation 1 and 2 are known as level equations. Continuing with the discussion of difference equation, A difference equation may be then obtained by subtracting equation 2 from equation 1, which is obtained as delta yt is equal to beta 2 delta xt plus delta ut. This is our equation 4. It can be shown that if the error term does not exhibit serial correlation in equations 2 and 3, then the error term in equation 4 will be serially correlated. All these data transformation activities may cause the error terms to be correlated with each other. Moving on with the causes of autocorrelation, another is nature of time series data. If either the dependent variable or the independent variable or both are non-stationary, then the error term in the regression model will exhibit serial correlation. Last cause which we will study is the measurement error in dependent variable. Sometimes the variables in the data are measured inaccurately so that the reported values are different from the true values. If the dependent variable is suffering from measurement error, then this effect will get incorporated into the disturbance term. So each successive value of the disturbance term will exhibit some systematic relationship with the contiguous error term, causing the model to suffer from autocorrelation. Continuing with the above discussion, if yi star is equal to yi plus vi, where yi star is measured value and yi is the true value, so the true model is yi is equal to beta 1 plus beta 2 x2i plus so on up to beta k xki plus ui. But the estimated model is yi star is equal to beta 1 plus beta 2 x2i so on up to beta k xki plus ei. So the disturbance term in the estimated model ei is equal to ui plus vi. If there is a systematic measurement error in y, then the successive vi terms will have a systematic relationship with each other, causing the ei terms to exhibit autocorrelation. Now we will study the different natures of autocorrelation. Autocorrelation is classified as positive and negative depending on the relationship between successive disturbance terms. First, we will discuss the positive autocorrelation. If the covariance between ut and ut minus 1 is positive, then autocorrelation is said to be positive. It also means that a positive disturbance term is followed by a positive disturbance term and a negative disturbance term is followed by another negative disturbance term. Second is negative autocorrelation. If the covariance between ut and ut minus 1 is negative, then a positive disturbance term is followed by negative disturbance term and the negative disturbance term is followed by a positive disturbance term. In this case, the autocorrelation is said to be negative. Now we will study the order of autocorrelation, which is being decided on the basis of the following. The relationship between successive error terms and upon the number of lags with which the disturbance in a given time is a function of the disturbance in the previous time periods. Let us start with the first order autocorrelation. When the disturbance in any one time period is a function of the disturbance with one time period lagged, it is called first order autocorrelation. The relationship between a pair of successive disturbance terms is given as ut equal to rho ut minus 1 plus epsilon t, where rho is the coefficient of autocorrelation such that modulus rho is less than 1, and epsilon t is identically and independently distributed normally with mean 0 and variance sigma square for all value of t. This above process is also called first order autoregressive process or AR1 process, and this series of UT is also known as the white noise series with zero mean. It is helpful to have the absolute value of rho, the coefficient of autocorrelation, to be less than 1 for the stability of the autoregressive process. If the absolute value of rho is greater than 1, then the series would be explosive. The magnitude of rho indicates the strength of autocorrelation. The closer is the magnitude of rho to 1, the stronger is the autocorrelation. Further, if rho is greater than 0, autocorrelation is positive, and if rho is less than 0, autocorrelation is negative. Next is higher order autocorrelation. The longer the time period of the relationship between the disturbance term in the current time period and the disturbance term in the previous time periods, the higher is the order of autocorrelation. The order of autocorrelation would depend on the nature of data. For example, in the case of quarterly data, a fourth order autocorrelation is more likely to occur, and in case of monthly data, a 12th order autocorrelation is more likely. Third is the second order autocorrelation or AR2, which is the disturbance in period T is related to both the disturbance term in period T minus 1 and the disturbance in period T minus 2. In this case, mu t is equal to rho 1 into mu t minus 1 plus rho 2 into mu t minus 2, so on up to epsilon t. The assumptions about the disturbance of epsilon t and the magnitude of rho t remains as in the AR1 process. The last is the pth order autocorrelation. In general, the autocorrelation may be of any order, and a pth order autoregressive process ARP may be written as ut equal to rho 1 ut minus 1 plus rho 2 ut minus 2 plus rho 3 ut minus 3, so on up to rho p into ut minus p plus epsilon t. The assumptions about the distribution of epsilon t and magnitude of rho t remains as in AR1 process. Now we will study the different consequences of the autocorrelation on the regression coefficient. First is the estimates of regression coefficients that are unbiased and consistent, but not efficient. Let us see the proof of unbiased regression coefficient. The OLS estimator of beta may be expressed as beta hat equal to covariance xy upon variance of x. Now this is equal to beta plus covariance xu upon variance of x. This implies that expected value of beta hat is equal to beta because covariance between x and u is equal to 0. Hence, the estimates of regression coefficients are unbiased even in the presence of autocorrelation. Second consequence of the autocorrelation is that the variances of the regression coefficients are also biased and inconsistent. Proof for bias in the variance of the regression coefficient is given here. We know that beta hat OLS is equal to sigma xi yi upon sigma xi square. Therefore, variance of beta hat OLS is equal to sigma square upon sigma xi square. So when no autocorrelation is present, rho is equal to 0 and variance of beta hat is unbiased. When autocorrelation is present, which means rho is not equal to 0, then variance of beta hat is biased, and it can be shown that under AR1, variance of beta hat under OLS is now equal to sigma square upon sigma xt square into 1 plus 2 rho into sigma xt into xt minus 1 upon sigma xt square plus 2 rho square into sigma xt into xt minus 2 upon sigma xt square, so on up to 2 rho n minus 1 into x1 into xn upon sigma xt square. So if rho is greater than 0, that is when positive autocorrelation is present, then OLS will underestimate the true variance. If negative autocorrelation is present, then rho is less than 0, then we will find that OLS will overestimate the true variance. The third consequence of the autocorrelation is the T and F tests are not reliable because of underestimation or overestimation of the standard errors of the regression coefficients. So when the true variance of the regression coefficient is underestimated, then the t values of the OLS estimates are larger than should be. As a result, one might conclude that the variables are statistically significant when they are not, and this is our type 1 error. On the other hand, when the true variance of the regression coefficient is overestimated, then the t values of the OLS estimates are smaller than it should be. As a result, one might conclude that the variables are statistically not significant when actually they are, and this is our type 2 error. Moving on to the fourth consequence of autocorrelation, which is that the estimate of the variance of the error term is also biased. Now this can be seen in the following manner. For a simple linear regression model, if variance of each ui is given as sigma u square, then its estimator sigma u hat square is given as sigma u hat square is equal to sigma ei square upon n minus 2. Since expected value of sigma ei square is equal to n minus 2 sigma u square, therefore sigma u hat square becomes an unbiased estimator of sigma u square. But if autocorrelation is present, then for a large n and first order autocorrelation with parameter lambda, then expected value of sigma et square is equal to sigma u square into bracket n minus small bracket 1 plus 2 rho sigma xt into xt minus 1 upon sigma xt square
plus 2 rho square sigma xt into xt minus 2 upon sigma xt square, so on up to 2 rho raised to the power n minus 1 into x1 into xn upon sigma xt square, bracket closed. Then expected value of sigma et square is equal to sigma u square into n minus 1 plus rho lambda upon 1 minus rho lambda, in which case the estimator sigma u hat square becomes a bias estimator of sigma u square. The last consequence of the autocorrelation is that as a result of the bias in the estimated variance of the error term, the R square values will not be a reliable test of goodness of fit. If autocorrelation is positive and the independent variable is growing over time, then the estimated variance of the error term will be underestimated and the value of R square will be overestimated, implying an exaggerated goodness of fit. Similarly, when negative autocorrelation is present, goodness of fit will be underestimated.
Slide 48. Autocorrelation is the presence of covariance between the error terms in the contiguous observations in the regression model. They could arise due to autoregressive error terms or error terms which are generated as a result of moving averages. When the error terms of a given observation is correlated to the error term of the immediately succeeding observation, autocorrelation of first order is said to be present. The higher order autocorrelation is said to be present when the error terms are correlated across observations with a greater time lag. Autocorrelation could be positive or negative. Now, there are several factors like time series nature of data, model misspecification, measurement error in the dependent variable, cobweb phenomena, lag dependent variable, etc., that may give rise to autocorrelation. The estimates of regression coefficients are unbiased, but they are not efficient in the presence of autocorrelation. The variances of the regression coefficients are biased and inconsistent, and the hypothesis test and tests of goodness of fit are unreliable in the presence of autocorrelation.